Imagine we have a stationary coordinate system and we label this stationary coordinate system as C and let f of x represent the shape of an arbitrary profile. To mathematically represent a wave, we denote it with psi as a function of x and time. Let's assume that at time equals 0, the wave has a shape of f of x. After some time t, the profile has moved along the x-axis with the distance v times t. Here, v is the speed of the motion. Let's now introduce a coordinate system that travels along with the profile. Let's label this coordinate system as C'. In C' coordinate system, the psi function is no longer a function of time. This is because the profile looks stationary in C'. Here, the coordinate system is x' instead of x. But we wish to rewrite this expression in terms of x so that the profile can be described by an observer who is in the stationary coordinate system or in the C coordinate system. To do this, observe that a point on the profile has a distance x' when viewed from the C' coordinate system. While in the stationary coordinate system, this distance will be equal to x. Using these relationships, we can write x' as x' equals x minus vt or velocity times time. And we can plug this back to psi so that psi is now a function of both space and time. And this structure represents the most general form of the one-dimensional wave function. And now that we are familiar with this equation, what is the significance of knowing this structure? The answer is when we have any arbitrary stationary profiles and we want it to move to the direction of the positive x-axis, we simply change its dependent variable x into x minus vt. For example, we have psi equals x squared, and if we want to make it move along the positive x direction, then we simply need to change x into x minus vt. Another example is psi equals x cubed. If we want to make it move along the positive x direction, then we simply need to change x into x minus vt. If we have sine of x, whose domain by default is from negative infinity to positive infinity, then we just have to change its argument from x to x minus vt, then it will begin to move with the speed v. If we want the graph to move in the opposite direction, we simply switch the sign of the velocity v. In our case, change the negative sign to positive, and the profile will move in the opposite direction. So recall the relationship between stationary and moving coordinates. X' is equal to x minus plus wave speed times time. Let's label this as equation 1. So if we take the derivative of x' with respect to x, we have a value of 1. Let's label this as equation 2. This time, if we take the derivative of x' with respect to time, we have partial of t of x minus plus wave speed times time. So we have negative positive wave speed. Let's label this as equation 3. So going back to this expression, recall that our function for wave is a function of x and time. Let's label this as equation 4. So using this expression, we could rewrite the argument of f of x and t as f of x' since x' is a function of both x and time. Let's label this as equation 5. So while we are at psi of xt equals f of x prime, what does partial of psi with respect to x looks like? So to do this, since psi is equal to f, partial of psi over partial of x is equal to partial of f over partial of x. Using chain rule, we could also write this as partial of f over partial of x prime times partial of x prime over partial of x. However, using the results of equation 2, partial of x prime over partial of x is equal to 1. Hence, this term is equal to 1. Therefore, partial of psi over partial of x is equal to partial of f over partial of x prime. For now, let's label this equation as equation 6 and this one as equation 7. Now this time, let's hold x constant and let's get the partial derivative of psi with respect to time. Again, using the chain rule, this is also equal to partial of f over partial of x prime times partial of x prime over partial of time. But then again, if we look at equation 3, partial of x prime with respect to time is equal to negative positive v. Therefore, this term here is equal to negative positive v. Hence, partial of psi divided by partial of t is equal to negative positive v times partial of f over partial of x prime. Let's label this equation as equation 8. So note that we can plug equation 7 to equation 8. And we end up with partial of psi over partial of t equals negative positive v partial of psi over partial of x. Let's label this as equation 9. Now at this stage, I would like to point out that the wave with constant speed v are completely described by a constant amplitude and a constant wavelength. So normally, two constants appear when you solve a second order differential equation. So to arrive with this consistency, let's try to write the second partial derivatives of equation 7 and 8 and then combine them just like what we did for equation 9. So starting from equation 7, let's get partial of x of partial of psi over partial of x. And this is equal to partial over partial of x of partial of f over partial of x prime. Again, this was obtained by applying partial of x to both sides of equation 7. So this side can be written as second order partial derivative of psi with respect to x. And this is equal to, again, we can apply the chain rule here. So we have partial over partial of x prime of partial of f over partial of x prime times partial of x prime over partial of x. Again, using equation 2, this is equal to 1. And we end up with the second order partial of psi with respect to x, which is equal to second order partial of f with respect to x prime. Let's label this as equation 10. And now let's get the second order partial derivative of equation 8 by applying partial divided by partial of t to both sides of equation 8. We could actually write this as the second order partial of psi with respect to time, which is equal to, I could put this outside the partial differential operator since v is constant in our case. Again, we can use the chain rule. So we have partial of x prime applied to partial of f over partial of x prime times partial of x prime over partial of t. Again, this is equal to negative positive v based on equation 3. So note that negative positive v times negative positive v is equal to v squared, regardless whether both v are negative or positive. The second order partial of psi with respect to time is equal to v squared times the second order partial of f with respect to x prime. So for now, let's label this as equation 11. So here we could plug equation 10 to equation 11. And we end up with second order partial of psi with respect to time is equal to v squared second order partial of psi with respect to x. Now, we have derived the one-dimensional differential wave equation. So as an example, given v equals omega over k, here v is the wave speed, omega is the angular frequency, and k is the wave number. Show using brute force that psi of x t equals a sine of k quantity x minus vt is a solution of the differential wave equation. So while we have this equation, let's distribute k over the argument x minus vt. A times sine of kx minus kvt. So, but then again, using this equation, kv is actually equal to omega. Hence, we could further simplify this expression by writing psi of xt equals a times sine of kx minus omega t. So to prove that this is a solution to the differential wave equation, we first get the second order partial of psi with respect to x, and then the second order partial of psi with respect to time, and see if this expression checks out. First, let's get the second order partial of psi with respect to x. So let's get first partial of psi divided by partial of x. This is equal to partial over partial of x of a sine kx minus omega t. This is equal to a times cosine kx minus omega t times the derivative of the argument, which is k. So this is equal to ak cosine kx minus omega t. So this is equal to partial of psi over partial of x. Next, let's get the second order partial of psi with respect to x. And this is equal to partial of x of partial of psi over partial of x, which is equal to partial of x of this expression, which is ak cosine kx minus omega t. And this is equal to ak times negative sine of kx minus omega t times k. So the second order partial of psi with respect to x is equal to negative a k squared sine of kx minus omega t. Let's now find the expression for the second order partial of psi with respect to time. Let's write partial of psi with respect to time. This is equal to partial of over partial of t of a sine of kx minus omega t, which is equal to a times the derivative of sine, which is cosine kx minus omega t times the derivative of the argument, which is times negative omega. So we have negative a omega cosine kx minus omega t. Let's calculate the second order partial of psi with respect to time, which is equal to partial over partial of t of partial of psi over partial of t. So this expression is just equal to this expression. So we have partial over partial of t of negative a omega cosine kx minus omega t. The second order partial of psi with respect to time is equal to negative a omega times negative sine kx minus omega t multiplied to the derivative of the argument with respect to time, which is negative omega. The second order partial of psi with respect to time is equal to negative a. This is because we have three negatives here. So negative a omega square sine kx minus omega t. And while we have this equation, let's multiply both sides of the equation with 1 over v squared. So we have 1 over v squared second order partial of psi with respect to time is equal to negative a omega square over v square sine kx minus omega t. But recall that the wave speed v is equal to angular frequency divided by k. Therefore, this factor is also equivalent to k squared. 1 over v squared second order partial of psi with respect to time is equal to negative a k square sine kx minus omega t. If we compare this with this one, they are equal. Therefore, the second order partial of psi with respect to x is equal to 1 over v squared second order partial of psi with respect to time. And this tells us that this equation is a solution to the differential wave equation. So for your quiz, given v equals omega over k, where v is the wave speed and omega is the angular frequency and k is the wave number, show using brute force that psi of xt equals a cosine of kx minus omega t is a solution of the differential wave equation. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!